Okay, so the last speaker of today is Vincent Colin from Nantes, and he will talk about Birkhoff sections and Reeb chords in 3D contact manifolds.
Okay, thank you very much. I want to thank the organizers for the invitations. I'm glad to be back in Rio after 20 years exactly. So time has passed, alas, but it's still as fantastic as I remember it. So indeed, in this talk, we will be interested in the dynamics of Reeb vector field on three-dimensional contact manifolds, and I will report on a joint work with Umberto Riniewicz and Anna Reichmann, together with some contribution of Pierre Dehornois. So maybe to fix notation first. So M will be a oriented closed three-manifold. Xi will denote a co-oriented contact structure on M, so defined by a globally defined as a kernel of a one form alpha, so that alpha with G alpha is strictly positive. And R will be a Reeb vector field that is a vector field which is transverse to the contact plane, positively transverse, and whose flow preserves the contact plane. And as you know, and as it was recalled by Victor, such Reeb vector fields are in one-to-one correspondence with contact form, with equation of Xi, and the one-to-one correspondence is given by the solution of the system, the unique solution of the system, that alpha evaluated on R is 1, and R is in the kernel of D alpha. Okay. And one main example that we have in mind, or one example we have in mind, is the case of the geodesic flow on a surface here. So if sigma g is a Riemannian surface, then the geodesic flow, which is a flow on the unit tangent bundle of sigma, with the contact form, the contact structure, with the standard contact structure, which is the Liouville contact structure, it is a Reeb flow. So the geodesic flow is Reeb in that case. Okay. So the first thing I want to do before stating new result is to recap older ones. So it all starts for me with, or for the purpose of this talk, it starts with the proof of the Wenching conjecture by Taubes. So every Reeb flow, every Reeb vector field on a three-manifold has a periodic orbit, which is already different from like even volume-preserving flows. And moreover, not only it has one periodic orbit, but it has at least a two. This was proved by this was proved by Cristofaro Gardiner, Hutchings, and Pomerleano. Or was Pomerleano in the thing? I don't know. No, Cristofaro Gardiner and Hutchings. Sorry. Okay. The next result was that not only you have always more than two, but there is a dichotomy. The dichotomy is that when the Reeb vector field is non-degenerate, then you have either two periodic orbits or infinitely many. And so this was proven first in the case of S3 on the 3-sphere by Hofer, Vysocki, and Zender. Then, on manifold where the contact structure is torsion by Cristofaro Gardiner, Hutchings, and Pomerleano. And for general non-degenerate Reeb flows by myself, Pierre d'Ornois, and Anna Reichmann. Okay? And now we even have the degenerate case, which is treated at least partially by Cristofaro Gardiner, Umberto Riniewicz, Michael Hutchings, and Liu, in the case where the contact structure has a C1, which is torsion. And so, again, this is Cristofaro Gardiner, Riniewicz, Hutchings, and Liu. Okay. So now if we want to go beyond the study of periodic orbit, we proved with Pierre d'Ornois and Anna Reichmann that moreover, if the Reeb vector field is generic, C-infinite generic, then you have positive topological entropy. So C-infinity generically, the Reeb vector field has strictly positive topological entropy. Which means, in the case of a three-dimensional manifold, that actually there exists a homoclinic connection after Katok. So what is a homoclinic connection? A homoclinic connection is a transverse intersection, in our case, between stable and unstable manifold of the same hyperbolic orbit. So you have an hyperbolic orbit of the flow. You have the stable and you have the unstable manifolds. And these two intersect, which means that there exists an orbit which at minus infinity is asymptotic to the hyperbolic orbit, and at plus infinity goes back and is asymptotic to the same orbit. Okay? So if you wonder about this genericity assumption, actually, for example, when M is not a graph manifold, it's enough to have the Reeb vector field non-degenerate. Okay. So, for example, if you have a three-dimensional hyperbolic manifold, every non-degenerate Reeb vector field has positive topological entropy. Now you want to know more. So the next thing is the existence of a Birkhoff section, again for generic Reeb vector field. So again, generically, a Reeb vector field has a Birkhoff section. So there are two different hypothesis that leads to this consequence. The first one was given by myself, Pierre d'Ornois, Umberto Riniewicz, and Anna Reichmann. And the hypothesis is that the Reeb vector field has to be non-degenerate, plus the volume form alpha OHD alpha has to be approximated by periodic orbit. Which is a generic condition by Irié. What? As a measure, yeah. And the second hypothesis is the fact that the Reeb vector field is still non-degenerate, and as we say, it is Kupka-Smell, which means that you have transversality of all the stable and unstable manifold. And this was obtained by Contreras and Mazzucchelli. So Contreras and Mazzucchelli. Non-degenerate plus Kupka-Smell. And again, Kupka-Smell means that the stable and unstable manifold of every hyperbolic orbit intersect transversely. Okay, so far so good. And the last result, the last result I would like to mention is the fact that now if you are interested in Reeb chords, which is in my title, then you have a proof of the so-called Arnold conjecture by Hutchings and Tubbs, which tells you that for every Legendrian, every closed Legendrian curve has a Reeb chord. So if you take any Legendrian, I remind you that a Legendrian is just a curve which is tangent to the contact plane everywhere. Then you find a portion of Reeb orbit which starts and ends on the Legendrian L. Okay. So these are the results I would like to extend. Maybe at this point I should remind you also what a Birkhoff section is, just to make sense of this statement. So Birkhoff section for the Reeb flow R, it is a compact immersed surface with boundary. So it's compact immersed surface S, so that the interior of S is embedded, plus it is transverse to the Reeb flow, and the boundary of S is a collection of periodic orbits, so it's tangent to the Reeb flow. Okay, these are the, let's say, A and B condition, and there is a third condition, which is the fact that any orbit of the flow intersect the surface in bounded time. So every, let's say, for every x in M, phi t of x intersects S for some t smaller than a universal large T. Okay. So here maybe you're wondering how this is possible. So what is condition immersed and then embedded? What happens is that you could have, first of all, two different boundary components of S that go to the same periodic orbit. And moreover, you could have a boundary component of S that is winding around several times the same periodic orbit before, okay, so. But this is the Birkhoff section, and so a Birkhoff section is very important and useful to have one, because once you have a Birkhoff section, you can consider the first return map on the section, okay, and this completely reduces the dynamics of the Reeb flow to the one of the surface diffeomorphism, which is just the first return map. Okay? And so then you have many results for surface diffeomorphisms, and this object allows you to transfer all the results you know for diffeomorphism of surfaces to Reeb flows. Okay? So that's why we are really looking for Birkhoff sections. So now let me tell you about new results. So I will pack them all in one statement. There are actually 3 statements. The first one, so all the statements will all like generically. So the first one is telling you that generically on the Reeb flow, not only there exists a hyperbolic orbit with a homoclinic connection, but it tells you that every hyperbolic orbit has a homoclinic connection. So generically, on the Reeb vector field, every hyperbolic orbit has a homoclinic connection. And a homoclinic connection in every pair of its stable and unstable manifold. You have kind of 2 stable and 2 unstable manifold. If you choose any pair, stable and unstable, you will find a homoclinic orbit in this pair. Okay, an intersection point between these 2. Okay. The second result will improve the existence of Birkhoff sections. And it will tell you that not only you can find a Birkhoff section, but you can find a Birkhoff section that is embedded. Okay? And you can even impose any collection, any finite collection of periodic orbits to be in its boundary. And basically every finite collection of Legendrian to be inside the section. This last part is not exactly true. You have to slightly move them, but so the precise statement is the following. So generically, on the Reeb vector field, there exists an embedded, and given a collection gamma of periodic orbits of R and of closed, a finite collection, and of closed Legendrians, L, there exists an embedded Birkhoff section S such that gamma is in the boundary of S, and there is some L prime which is Legendrian isotopic by a C0 small isotopy to L, so that L prime is inside the Birkhoff section. Okay? So here the thing is that you fix, so you have a generic condition on R that I will not express, but it's the kind of properties that I already mentioned, like non-degenerate plus, you can list the properties you need. Once you have a Reeb vector field which meets this property, given any collection of periodic orbits, for example, you can find a Birkhoff section that contains these periodic orbits in its boundary. Okay? And moreover, you can even impose like some Legendrian or a small deformation of a collection of Legendrian to be inside the Birkhoff section. Okay? This result is kind of mimicking the similar result by Giroux on open books, where you have a result telling you that if you take a contact manifold, 3-dimensional contact manifold, picking any collection of transverse curves and of Legendrian, you can find an open book decomposition whose binding contains these transverse curves and the page contains the Legendrians. Okay, so this is a kind of similar result, but here the difficulty is that the Reeb vector field is fixed. Okay, once for all. Once it is fixed, then for every collection of orbits and every Lagrangian, you can find a Birkhoff section. Okay, but you don't have, once you have this genericity property, you don't move, you don't touch the Reeb vector field anymore to find this Birkhoff section. And the last result has to do with Reeb chords, where we improve the kind of proof of the Arnold conjecture by Hutchings and Tubbs, this time for, in some sense, generic Reeb vector field, in the sense that we assume they have Birkhoff sections. So if a Reeb vector field has a Birkhoff section, then every Lagrangian has not only one Reeb chord, but has infinitely many Reeb chords. This is the first thing. The second thing is that if, moreover, you assume that the Reeb vector field has infinitely many periodic orbits, then every Lagrangian has infinitely many disjoint Reeb chords. And I will comment on this on the difference between these two statements. And finally, if you are allowed to move a little bit the Lagrangian, because in this statement, for the moment, the Lagrangian are fixed, you cannot move them, but if you are allowed to move them by C infinity small Lagrangian isotopy, then you get that there are infinitely, I mean, not only infinitely many Reeb chords, but the number of Reeb chords is growing exponentially fast with the action. So if L is allowed to be deformed, then by a C infinity small Lagrangian isotopy, then the number of Reeb chords has exponential growth. And this is for generic, okay, for generic R. Okay. So let me comment on the difference between these two. So the thing is that you could have a Lagrangian that intersects a periodic orbit of the Reeb vector field. And in this case, the periodic orbit in the first statement would count for infinitely many Reeb chords, because you can go around several times. Okay, you have longer and longer Reeb chords. So in this first statement, the Reeb chords are not necessarily disjoint. You can have Reeb chords that wind around several times a periodic orbit. Okay, and this is a source of infinitely many Reeb chords. Whenever you have infinitely many periodic orbits, then you are sure to find this time infinitely many disjoint Reeb chords that can be either like this or even possibly on periodic orbits, but in that case you would have infinitely many disjoint. You could have infinitely many periodic orbits intersecting the Reeb chord. And at this point, I realized that I forgot to mention two things when I was explaining previous results. I wanted to go to the new one, so I forgot two things. The first thing is that in the two or infinitely many periodic orbit alternative, we completely, in some sense, understand the case where there are only two. And if you have only two periodic orbits, it means that the ambient manifold is either the three-sphere or a length space. Okay? And you have a Birkhoff section, which is either a disk or an annulus. Okay? And if it's a disk, if it's an annulus, for example, it will be a the first return map would be a pseudo-rotation. So we kind of understand completely this case. Okay? So the second result tells you, for example, that as soon as the ambient manifold is not S3 or a length space, then every Legendrian has infinitely many disjoint Reeb chords. Okay? And the only hypothesis is the fact that you have a Birkhoff section, which I remind you is a generic condition. So the result, again, if I insist a little bit, is that if you have a Reeb vector field that has a Birkhoff section, this is a generic condition, now your Reeb vector field is fixed. Once it is fixed, for every Legendrian, you have infinitely many Reeb chords. But you are not allowed to move the Legendrian. Okay? When the Reeb chord is, when the Reeb vector field has a Birkhoff section, you don't move anyone anymore. And I mean, you are not perturbing. And for every Legendrian, you have infinitely many Reeb chords. Okay? And if you are allowed to move the Legendrian, basically you would find exponential growth. Okay.
Sorry, these infinitely many Reeb chords would also be just one Reeb chord?
No, not in that case, when they are disjoint. In that case, yes. And indeed, this happens if you, maybe I can mention this. If you are in the special case of the three-sphere, for example, with a Birkhoff section or an open book, which consists of, so the boundary is two periodic orbits, and then let's say the first return map is an irrational rotation. Okay? In that case, you can double the page. So this is the page which is an annulus. I have one periodic orbit gamma 1, gamma 2. Otherwise, the first return map is an irrational rotation. Okay? You can double the page, take the kind of the opposite page, and then it's easy to find a Legendrian which is crossing the doubling like this, which is a 2 torus. Okay? And then the only chord it has are the two periodic orbits. Otherwise, since you have irrational rotation, you don't have any chord in this region. Okay? This situation happens, but this is basically the only case where it happens. Otherwise, you have infinitely many chords. Okay, so this is one point. And the second point I forgot to mention, I'm doing it now, is that in the case of geodesic flow, we have a result of Alves and Mazzucchelli, which tells you that every geodesic flow has a Birkhoff section. Okay? So in particular, in that case, the theorem applies, okay? Which means that every Legendrian has infinitely many Reeb chords. And since you also have infinitely many periodic orbits, there are infinitely many disjoint Reeb chords. Okay? And so, for example, in the case of the two spheres, you can obtain, of course, a complicated new proof of a classical result of Serre from the 50s, that if you consider a sphere with any metric, you take a point in the sphere, and as a Legendrian, you can consider the fiber over this point, which is a Legendrian. Okay? And then the Reeb chords exactly correspond to geodesic loops, which are loops that start at this point and come back to this point. Of course, a priori not with the same tangent vector. Okay? These are exactly the Reeb chords. And so the theorem of Serre tells you that indeed you have infinitely many such geodesic loops based at one point. But of course, this result we get is more general because the Legendrian can be any Legendrian. So in that case, you would get in a general surface, but it's typically easier when there is genus, so we can stick with the sphere. But anyways, so if you take the sphere, you can take any Legendrian. So what is the projection of a general Legendrian? You can think of as an immerse curve with maybe some cusps. And you can also have corners. Corner means that you arrive to there, and then you follow the fiber for some time, the Legendrian fiber, and then you exit. So in between, you have your Reeb vector field has been rotating. Okay, so when you exit, after following the fiber for some time, you exit with a different angle. And you could have something like this. Okay? And so for any such curve, you would find infinitely many geodesic loops that start on the curve and end on the curve. And when you have angles, you are allowed to come and arrive in some kind of sector like this, okay, which correspond to the angle that the Reeb vector field is just following when you go along the fiber. And this has to be cooriented to make sense. Okay. So you have such a result. Okay, so Serre's theorem was proven by a min-max procedure. Probably you can also apply the min-max procedure in that case, even though it might be slightly more difficult to put in place. But okay, anyways, you get the result by just applying this general theorem. Okay. Do you have any questions before I explain some of the proofs? Yes? Because for a metric, you would get infinitely many periodic orbits. But you have infinitely many periodic orbits with the round metric, which are all the great circles. Yeah. You always get infinitely many these ones. Okay, so I will select some parts of the proof, the ones that I enjoy the most. The first thing is about the existence of homoclinic connections for every hyperbolic orbit. This, I will not say basically anything, apart from the fact that it's a typical case where you can use the existence of a Birkhoff section to transpose surface diffeomorphism results to the case of Reeb flows. So to prove this thing, we first assume that there is a Birkhoff section, which is a generic property, and then we apply the relevant result of Le Calvez and Sambarino, which is exactly giving you this conclusion. So for the first part, which was called, maybe it was not called, but the first part is first, so generically, R has a Birkhoff section, which means that you have a first return map and then apply Le Calvez and Sambarino results to get the conclusion. So this is typically the case. You have to adapt a little bit because here you have a surface with boundary essentially, and when you want to work with closed surface, so the Le Calvez-Sambarino result is for closed surface. So what you do is you blow down the boundary, but then your map is not completely smooth, so you have to adapt a little bit, but still you can adapt. Okay, so I will not say more on this. And I will move to the second part, which is the existence of nice Birkhoff sections. Nice means embedded, that contains a given set of periodic orbits in the boundary, and which basically contain any given Legendrian link after small deformation. Okay, so how do you get something like this? Well, so you need to be sufficiently generic, and sufficiently generic for us will be that the first property is realized. So you have every hyperbolic orbit as a homoclinic connection. And moreover, if you follow Irie, you can even assume that hyperbolic orbits are dense. So let's say assume R, first of all, as a Birkhoff section. Every hyperbolic orbit as a homoclinic connection, and hyperbolic orbits are dense. This is by, let's say, Irie plus maybe Cam theorem, because it tells you that in the neighborhood of every elliptic, you also have a hyperbolic. Okay, so you assume this. And now you would like to make sure that any collection of periodic orbits can be put in the boundary, and that every Legendrian can be put inside the surface. And for that, you have one main tool, which is a building block. And our building block will be what is called freed pair of pant. Okay? So basically, for finding surfaces of sections, you have several tools. The first one we use to prove the existence of Birkhoff sections is a more sophisticated holomorphic curve theory. Typically, when you have a holomorphic curve, the projection is transverse to the Reeb flow, so it gives you a section. In the case of geodesic flows, you have what are called Birkhoff annuli. If you have a closed geodesic, over the closed geodesic, you have an annulus of section. And the last tool, the last building block are these freed pair of pants that I can try to describe a little bit now. And these are the ones we are going to use. So freed pairs of pants. So freed pairs of pants, they will be constructed in a neighborhood of a homoclinic connection. So first of all, maybe I already mentioned it, but I'm not sure. So I define for you what a Birkhoff section is. Birkhoff sections, there are three properties. The boundary is made of periodic orbits, the interior is transverse to the flow, and then every orbit intersects the Birkhoff section in finite amount of time. If you get rid of this third condition, what you get is just a surface of section. Okay? So surface of section and freed pairs of pants will be surfaces of section. So they are just, the interior is transverse to the flow, and the boundary is made of periodic orbit, and that's it. You do not ask them to intersect every orbit in the flow. Okay? So how do you construct a Birkhoff freed pair of pants? This is coming from the fact that whenever you have a homoclinic connection, well, you see a horseshoe in the dynamics. So if I take a hyperbolic orbit, H, with a homoclinic connection, I can take a transverse disk. So I have the stable and unstable manifolds that intersect the disk into like small interval like this. Okay? And I have a homoclinic connection, which means that these stable and unstable manifold intersect somewhere. Okay? And so what happens is that this is the usual horseshoe picture. Now if I draw my transverse rectangle like this, I can draw the stable and unstable manifold, the intersection of the stable and unstable manifold, and I have some intersection somewhere. Okay? But let's say it's like this. So if I iterate forward, which means if I push this intersection, if I flow this intersection by the Reeb flow, what I'm going to see is that this thing is going to enter, and so it is going to accumulate to the unstable manifold. And the other way around, when I take this intersection and I flow it back, I iterate the first return map to this thing, then it's going to it's going to accumulate on the unstable manifold. And this means that if I consider, like, in some sense, this rectangle, and I consider its image by the flow, so this part, when I iterate a lot, this is going to be contracted in this direction and expanded in the other direction. And what is going to happen is that this rectangle is going to come back, and the image of the rectangle iterated several times around the flow is going to come back like this, and then continue. Okay? And vice versa, when I iterate in the other direction, the red rectangle is going to come back like this. Let's say something maybe here. Okay? And when I see such intersection of rectangle, this is what is called the Smell horseshoe. Okay? And when you have such a picture, what you are going to find is, first of all, in this angle, you have the hyperbolic orbit. What you will find is, let's say, a periodic orbit in this, in this intersection of the blue and the orange. And then, by the hyperbolic dynamic behavior, you will find a periodic orbit which is passing in this intersection and then in this intersection, which means that you are going to follow this periodic orbit and followed by this one. And in some sense, what you get is a periodic orbit that intersects twice this rectangle. So if I draw the picture in 3D, what you see is a rectangle like this. I have one periodic orbit here, which is H. Okay. I have one periodic orbit here, which corresponds to this triangle. And then these 2 points are on the same periodic orbit. And if I flow basically this side by the Reeb flow, what I'm going to get is something like this. Okay? And similarly, if I flow what? If I flow this by the Reeb flow, what I'm going to get is something like this. Okay, these are my two. Okay. And in this picture, you are supposed to see a pair of pants, okay, which is made of these two kind of parts, which are called the, let's say, the ears of the pair of pants, which are, for the moment, tangent to the Reeb flow, and this central part, which is transverse to the Reeb flow. Okay. Once you see this picture, it's easy to turn it into a surface of section. You can move the interior to make it transverse everywhere, because you have some, if I draw it in one dimension, you have this horizontal part, which is like this, and then you have a part which is like that, tangent. And when you see that, it's easy to modify to make it transverse. Okay? So this pair of pants can be made can be turned into a surface of section. Okay? And so the good thing now with this pair of pants, these sections, is that they are everywhere, because we start from the hypothesis that the hyperbolic orbits are dense, and they all have homoclinic connections. Okay, so you have this kind of surfaces of section almost everywhere in your 3 manifold. And so maybe now let's see how you do to use them. So the next tool you need to use these kind of things is to say that if you have 2 surfaces of sections that intersect, possibly, you can resolve the intersection. This is called the Fried surgery or the Fried sum of two surfaces of sections. Why is that? Because if you have 2 surfaces of sections, you look at intersection points, for example, in their interior. And so let's say they intersect transversely like this. Okay, these are part of your surfaces of section. Oh no, this is, yes. Like this. So you see you have 2 surfaces that intersect transversely. The good thing with them is that they are both transverse to the Reeb vector field. Okay? You have a preferred transversal, which is the Reeb vector field. And once you have this preferred direction, you can desingularize, because if you want to, the result, the desingularization to be transverse, there is only one way of resolving the intersection. Okay, it's like this. In a 1D picture, the Reeb flow is like this, so this has to be resolved this way. There is no other choice which is reasonable. Okay, so once you have 2 surfaces of sections, you can take the sum, you can desingularize the union and get a new surface of section. So you may wonder what happens if you have some. Now you have a surface of section S like this, and it's intersect another surface, let's say S1 and S2, and this is the boundary of S2. Okay, the intersection is like this. This also you can desingularize till the end, and what happens is that what you see is like an helicoid when you resolve this thing. The new surface of section is as this as a boundary still, but it's rotating once around. Okay, you can resolve until the end, and what you get is something which is rotating. Okay, and what is good in your case is that if you start from a Birkhoff section, which is a special case of surface of section, and you take another surface of section, if you take the union of the 2 and you desingularize, you still have a Birkhoff section. Because the property is that every orbit intersects in bounded time. If you intersect S in bounded time, you will intersect, let's say, S in union S' in bounded time. And the resolution doesn't change anything, but just by a small amount of time. Okay? So the good thing is that if you have, again, a surface of section together with a Birkhoff section, the union of the 2, the desingularization of the 2, will still be a Birkhoff section. Okay? And so that's what you are going to do. You are going to start from your initial Birkhoff section, and you are going to add pair of pants to this Birkhoff section until you get the properties that you want. Okay? So, for example, if you have a periodic orbit, how do you put it in the boundary? Well, the easy case is when this periodic orbit is hyperbolic. Because if you have a periodic orbit H in your collection gamma of periodic orbits of the Reeb vector field, which is hyperbolic, as we've seen, H is contained in the boundary of a pair of pants. Okay? So you take this pair of pants, you add it to your Birkhoff section, you desingularize, and you get a new Birkhoff section which contains H in its boundary. Okay, so you say maybe something like S union or Fried P H contains H. Okay, so this is how you incorporate hyperbolic orbits. I will not say how you incorporate elliptic orbits, but basically elliptic orbits, when you have an elliptic orbit, you have many satellite hyperbolic orbits, and actually you can find like Birkhoff, annuli between those and add them to the Birkhoff section or to many copies of the Birkhoff section. So you have the same kind of procedure. Okay, so this is how you manage to put a given collection of periodic orbits in the boundary of the Birkhoff section. I won't tell you how you do it embedded. It's a game with Chinese theorem. It's some sort of easy arithmetics that you do. But I will tell you a little bit on how you put a Legendrian or deform Legendrian in the Birkhoff section. So now assume that L is a Legendrian curve, connected for now. It doesn't change anything. And you would like to find a Birkhoff section that contains maybe not L, but L prime, which is isotopic and close to L. Okay? So there are two steps to do that. The first step is that you first find so you have your initial Birkhoff section S. And what you do is you first find a Birkhoff section S prime that is disjoint from L. Okay? So how do you do such a thing? So of course what is not so fun is that L can intersect your Birkhoff section S like this. Okay? So what do you do when you have such a situation? Well, you know that hyperbolic orbits are dense. So there is an hyperbolic orbit which is passing close to this intersection point. Okay? And you know that near this hyperbolic orbit, and its homoclinics, you have a small freed pair of points like this. Okay? So now what you do, so this pair of points will intersect the surface S close to this intersection point. And what's happening is that you have these two ears that are living like this. They are the opposite kind of orientation. Okay? And of course, these ears are very long, so you could have like, they could come back like a lot of time intersecting this surface, but we have some quantitative thing which tells you that these ears are very thin. And the smaller you take this rectangle, the longer the ears are, but the smaller they are. Okay? The thinner they are. And so you take this freed pair of points, and you sum with S. And so you wonder what is happening near these intersections. Okay? So you have to figure out what's happening when you sum these. But if I would draw it in dimension 1, I would have something like this. So this is my ears that are leaving this small rectangle R is here. And here you have the surface. Okay? And you resolve. And the fact that the kind of orientation are opposite is what happens when you resolve is that you have something like this. Okay? And this is the picture you see if you intersect, for example, with a plane which is here. Okay? If you take a transverse cut like this in the middle of the two ears, that's what you see. Okay? And when you approach the boundary, what you see are some kind of helicoid things which are rotating here and here in opposite directions, and here in opposite directions. I don't know if you see this picture. But what's nice is that when you resolve here, you kind of create a small mouth hole. So your original Legendrian was somewhere like this. And now you can take your Legendrian and make it go through the hole. You can isotope the Legendrian so that it goes through the hole. And of course, it could have, then you could create, since you have many branches, you could have like many other intersections with your new thing. But these are very thin, and their characteristic foliation is basically transverse to the Reeb direction. So whenever you have the Legendrian which intersect here, you can move it by a C0 small isotopy, you can push it away. So you might create new intersections, but those are easily, you can easily get rid of them. Okay. So this is the first step. With this kind of thing, you get rid of intersections. So now you have a new Birkhoff section that does not intersect L anymore. And what you would like to do is now you would like to push the Birkhoff section S prime along the Reeb flow so that it contains L. Okay? What prevents you to do this is the following. So basically you have your new Birkhoff section S prime, and S prime decomposes the manifold into a product. Basically, if you cut the manifold along S prime, what you get is something like S prime times 0, 1, where the 0, 1 direction is tangent to the Reeb flow, okay? Like this. And if you would like to push S prime so that it contains L prime, that contains L, or you have been modifying, but anyways, what prevents you to do this is whenever you have a Reeb chord. Okay? If you have S prime here, and here you have this product region in the middle, you have L, which is here. Okay? What prevents you from pushing S to incorporate L is the fact, for example, that when you project L to S using the Reeb flow, you have double points. Okay? If you don't have double point in the projection, you can just move in the Reeb direction transversely so that now L is contained in your new surface. Okay? So what really prevents you is whenever you have some double points of the projection, or let's say said differently, a Reeb chord for L that does not intersect S prime. Okay? Because you don't care with very long Reeb chords that would intersect S prime, okay? Because this one you don't see in the product region. Okay? And so you have this Reeb chord, and again, what you are going to do is you are going to get rid of them by adding freed pair of pants, because you know that there is a hyperbolic orbit which is passing close by. And this hyperbolic orbit, you will be able to find some freed pair of pants. Okay? And maybe this horizontal part of the freed pair of pants is not intersecting this Reeb chord, but you can easily move the Legendrian by a C-infinitesimal isotopy, actually, so that now the Reeb chord is exactly over this horizontal rectangle. Okay, because the Legendrian, like this distance here is kind of fixed, everything is kind of compactly supported. You can deform like this, put a freed pair of pants in the middle, so that it intercepts all the Reeb chords. And once you do the addition, you get a new Birkhoff section, and it does not, and then again, it does not intersect the Legendrian after like eliminating extra intersections, and you don't have Reeb chords anymore. So now you can push everyone you can push the page of the Birkhoff section so that it contains your new Legendrian. Okay. So you repeatedly add freed pair of pants to get what you want. And I think I'm done, but okay. I wanted to say a word about the last results, about infinitely many Reeb chords, but only if you ask questions. Okay, I'm done. Thank you.